Hi, I decided this would be a good distractor for people who are having cabin fever because of the COVID-19 pandemic. It's also a distractor for me, not thinking about vent settings and correcting low sodiums. The strangeness of quantum mechanics appeals to many people of all backgrounds. I hope both persons as well as those with a physics background enjoy this topic. The topic deals with quantum phenomena occurring on a macroscopic scale. So that's neither at the size of the atom nor at the size of the universe where there are quantum mechanical phenomenon described. Um, the later presentations, this is just going to be part of the presentations, but we'll get more technical, and it's going to be based on a 2014 paper by our group. The paper describes uh, our proposed solution of how you generate macroscopic quantum systems. We'll talk about a little bit in this presentation why it's a hard thing to do, but it stems back to observations um, which I've had since the 1980s. Um, there are aspects uh, that both those who have a biology background or those who have a physics background probably aren't going to like because it relies heavily on a broad range of topics from complex adaptive systems, and I'm going to use for illustrative purposes bees and gut microbes as examples of what complex adaptive systems are, though not in this particular talk today. To path indistinguishable symmetry, identical particles, which is at the core of reality. Um, in the later talks, the solution will be framed in terms of quantum information systems. And my area, in terms of research, I am a physician, but my area of research, it, when it comes to quantum mechanics, is quantum optics. So I'm not an expert on quantum information systems, but I can I know enough to frame the lecture in terms of it. Um, but in biology, this quantum information system it would be analogous to um, first of all electrical information systems, but DNA. So if we look at DNA, RNA, and proteins, um, we can view them as containing the same information, slightly distorted, but in different forms. And so they're information carriers. So we frame it in terms of the information rather than the absolute structure to explain how we can achieve macroscopic quantum systems. Um, I believe this is the optional approach of the great problem of decoherence compensation, which we'll talk about. Um, and again, even though I don't work in this particular area. So in this particular presentation, I'll lay down the foundation not just for macroscopic quantum processes, but also why they're more likely to occur in biological systems, and that's going to come down to evolution and natural selection. For now, I would like to have macroscopic mean things that are of the size of the everyday world, whether it's a train, a human, an ant, rather than at the size of a subatomic particle or at the scales of the universe or the galaxy where quantum effects can be observed. Um, a critical point is that, and this really starts hitting with, okay, uh, um, quantum mechanics is very bizarre, and it's really the only branch of modern physics. But um, we live in a quantum world, but the world we see around us is the classical world, which is essentially a subset of the quantum world the physical laws we see around us are basically uh, are an approximation, and they occur. If I can give an analogy, if we look out on the ocean, it appears to be flat, but we know that the world is round. But the rate of change of the world's curvature is so slow that the approximation holds, and we can say that it is flat. And these classical laws that we know every day, that a particle can't be in two places at once, occur um, because of the unique nature of our small part of what constitutes reality. Now, this is neither part of my medical talks nor of the optical coherence tomography channel. Um, I'm best known for, besides medicine, developing OCT for imaging in non-transparent tissue. Um, at the quantum work that I do, I'll discuss a little bit later in this talk, but let's just jump into it. So again, my name is Mark Brezinski. This is usually my background slide that I present on my YouTube videos, but I don't think it's particularly relevant to this talk, and I don't think you're listening to this talk to listen to my background. So let's just start up with some of the oddities of reality. So this is half relativistic, half quantum mechanics, but in the Big Bang, space and time was created. So we're going to get to this point once we start using words rather than math. These approximations are limited. But another fact is, so no, space and time did not exist before the Big Bang. So it's not that a bunch of matter was sitting in some place we can call one location in the universe and just exploded and decided to spread around the universe. And then the other point, I sort of figured this out when I was in my 20s and was pretty happy that I discovered something original, only to find out that it had been known for like 40 years. But space-time is continuously being created. So the galaxies are separating not based on momentum, but they're being separated based on the creation of space-time. So the space-time, for anyone who is listening to this talk, is still, at the time of their birth, is still within the galaxy. It's spreading out, but it hasn't left the galaxy yet. And that's a difficult concept to deceive. Now, you can ask, why don't we fall apart? Well, we're held together by gravity and electromagnetic fields. And so, while the space-time spreads out in gravitational waves, we don't. So and I'm just giving examples of what the quantum world is like. And it, again, if you're not using math, any description you use with words is inadequate, but will do the best I can. So if you ask the question, how much time does a photon experience that has traveled 10,000 light years? The answer you're going to get from most people is 10,000 years. But the actual answer is none. It doesn't experience any time. And this is where relativity and quantum mechanics are sort of butt heads, because that space-time hasn't been created yet. So all photons and all particles, for that matter, are virtual. There is a creation involving energy, and there's a detection, and in between what we view as their existence, we're going to see when we get to path indistinguishability, is not defined. Now, this is going to be an important concept, is particles are capable, like photons or electrons, spreading across space-time, and they become non-localized. And this becomes, we're going to see in photosynthesis, this is why photosynthesis has an efficiency of 100%, but the best photocells we have a classical limit of 25%. So we'll address the concept then. If we look at a ball, why is a ball and not spreading in space-time or overlapping with other balls? To the question, is light a particle or a wave? The actual real answer is neither, in terms of what we view a particle is and what we view a wave is. For all practical purposes, there are really no particles, there's just interactions. And I know we'll get into more specifics here. I know these are pretty abstract, and we'll just get into more concrete examples. And then a critical part is the concept that two photons can become entangled if you have two photons, two electrons, and then spread them apart long distances. You do something to one, the other one changes with no signal in between, no matter how great the distance is. This is an overlap between the concepts of entanglement and non-locality. And non-locality is the core of the research I do, and so do a lot of people. And it's critical in everything from the function of a photocell to many of the electronic devices we use. In the second lecture, I'm really going to hit these topics aggressively with the Young's interferometer and go right into the concept of path indistinguishability, which is related to identical particles and symmetry. And that gets down to what is the reality we live into. As much as we want to think about it as an electron circling around a nucleus, that's not really what's occurring. So photosynthesis and magnetoreceptors, which I'll talk about in a moment, are the quintessential quantum systems that behave so their effectiveness is so much greater than anything we can achieve with classical physics. So this was the subject of a very long 2014 paper. I think it was cut from 20 to 17 pages. I had to find a journal that would publish it. And a lot of the quantum communication of equations more moved out of it. And so, besides, I will note through these some works from many groups spanning 100 years, but some of the foundations that we built up are based on three of our papers listed here in a paper by Dunn involving quantum entanglement of macroscopic objects. And they're going to become important. And again, the quantum field approaches I work in is with OCT or photon-phonon interaction, or more specifically, the largest area is the quantum properties of thermal second-order correlations. And you don't have to know what that means, and I'm not going to torture you with it. So quantum mechanics extends beyond classic laws. It can only be described accurately through mathematics. But this is the critical point, and it's also the frustrating point. No physical law exists which prevents quantum systems from occurring at the scale of a body. So why is it purely dogmatic? And if you present data suggesting a macroscopic system, a macroscopic quantum system, why do you meet such resistance? And why do people believe large quantum systems can only last on the order of less than a femtosecond, 10 to the minus 15 seconds? And the issue is the dogma surrounds both with the concept of a wet environment and reductionist approaches. So a wet environment means there's a lot of interaction. So wherever you are, you're sitting in your chair, you have the TV on, things are molecules are striking your body, and that process breaks down what we'll just roughly call the quantumness, this ability, for example, to spread over long distances. It forces an electron to show up in one spot. And this continuous bombardment, known as decoherence, is what gives us the impression the classical world is all there is. So and reductionist approaches mean a large part of physics experiments, and being a basic science in addition to a clinician, you love the idea of extending something you do in a test tube to much larger areas. And we're going to go, and that's not the way a lot of major discoveries occurred, whether it was DNA or photosynthesis, were top-down experiments. But if you take a classic reduction experiment, have a cesium atom in a superposition, it's in more than one place at once, in a vacuum state at 0 degrees Celsius, the temperature's out in deep space. Sure, that's going to break down fast. A photon gets through, or a neutrino gets through, or something gets through and breaks down your system. But I'm going to use the example of arachidonic acid and its life on a tabletop versus its half-life within a cell membrane as an example of of the many reasons we can extrapolate things from reductionists. So just because we cannot maintain quantum systems at these small levels in a vacuum at the temperatures of deep space does not mean they can't occur in wet environments. And so we can first point to photosynthesis, and people will say, well, it's a relatively small area. It's controversial whether you call this a mesoscopic system or a macroscopic system. Mesoscopic in the sense that it's bigger than an atom, but it can be called macroscopic, just like magnetoreception, which I'll describe in a little while, because it actually controls the behavior of the whole organism. But I mean, mesoscopic I think is the most appropriate term. So what is it about photosynthesis? So if we look at a photocell, light comes in, and I just drew a blank on the name of the person whose model this is, but it's described in a later slide, but Foster model. So what happens in photosynthesis is light is captured and it's converted to energy of an electron. So imagine you have light striking a photocell, not chlorophyll, or not dealing with photosynthesis, but just a man-made photocell. You dislodge an electron. The electron bounces around till it finds a receptor, and then it gets creates electrical energy. Now, the process that's inefficient. So the maximum achieved limit for that is about 25% efficiency, meaning the energy of the photon, you're only going to get 25% of that back. But photosynthesis is at 100%. So what happens? And an important paper from, it was either Nature or Science, I can't read this on the screen, I listed on it, which is where this figure comes from. So in photosynthesis, the electrons form, let's imagine we have photoreceptors, and they're available or not available for an electron. They can take an electron, but there's a fixed period of time before that electron leaves them. So we dislodge electrons, and they're floating up above, light does, and we're floating up above these receptors. But now imagine the electrons are delocalized. They're a blanket. They don't exist in one local area of that space over the photoreceptor. So as soon as a site becomes available that can take an electron, that area is sucked in to the photoreceptor of the blanket, the energy of one electron. And then this process is effectively perfect. So it's spread out as soon as an area becomes available, rather than have an electron bounce around looking for a receptor that's available. You just have a blanket that instantaneously responds. And for people who have a physics background, that description pretty much probably is killing you, but it's good enough for this talk. So then why doesn't this happen with golf balls? I mean, why don't we just get golf balls overlapping with each other? Why don't they delocalize? And it's this concept of decoherence. They're constantly being hammered by interactions. So each time there's an interaction or entanglement, then the atoms are localized in space. And being in this wet environment, uh, and air is still considered a wet environment, then it forces these golf balls to be golf balls and not to start diffusing their borders and overlapping with one another. So we can beat this if we can prevent the decoherence. And we can't put a lead shield around something and just stop the decoherence. It's not that simple. And we'll go into why in later lectures. But there are techniques that we did describe in the paper that come out of quantum information systems that allow us to do this. But I want to start off with a biological example, which both illustrates this concept of not using, which illustrates this concept of not using reductionism. The molecule in the figure is arachidonic acid. It's fish oil, the active component of fish oil. It's used to make compounds like thromboxane and prostaglandins. But its half-life, because of those double bonds on the table, it would be destroyed instantaneously by the oxygen. How long does it live in a cell membrane? Decades longer, because it's protected inside the cell membrane. Now that's a classical concept of shielding. We're going to need something far more creative to protect it in a biological system, but to protect our quantum systems. And even more, what biology offers us is natural selection produces these incredible things like the cell membrane that protects these molecules. And we're going to get into even more sophisticated systems. The field that's grown over the last 15 years of complex adaptive systems. And this one's going to be painful for the physicists because I'm going to illustrate it in another lecture in terms of bees or gut microflora. But these are systems that behave like they have intelligence when they don't. The regulation of temperature in a beehive from flapping of bee wings and how those systems derived. So a lot of major areas, and the ones we talked about here, were started with top-down experiments, which eventually got more and more reductionist. And as you get more and more reductionist, as you isolate things, eventually you're going to take a photosynthetic unit and reduce it to 25% efficiency if you keep isolating it and isolating it. But if you think about genetics, Mendelian genetics started off very top-down, dealing with large-scale organisms, and then got down to DNA. This is a lot of words. Sorry, I cut it out of a paper. I cut it out of my paper. So this sentiment it hasn't been lost on on all physicists. So Anderson and Glenn Mann, two Nobel Prize winners in particle physics, made this point, and they used the concept of chirality, that everything is in biology is left turned, and so we're almost everything, and said if you just built up from subatomic particles a universe, the concept of chirality would not arise. It's an emergent system, and is the term used for it. And you can even see farther back into the works of, for instance, when you read Thomas Aquinas, uh, who did a lot of based a lot of what he found on Aristotle, that they talked about very similar concepts, and the these two Nobel laureates, Anderson and Glenn Mann, um, they they were against the reductionist approaches and realized that top-down approach and looking at things from, I don't want to say holistic because that envisions a lot of other areas, new wave areas, but the whole system. So at the heart of pretty much every one of these talks is going to be non-locality. And if there's one rule that, if there's one thing you can say quantum mechanics is about and the basic nature of the universe, it's that it's non-local by nature, and that's hard for us to accept because everything around us is local. You know, I'm right now in Massachusetts and somebody's in California, and the concept that we can be connected with no signal in between is uh, is hard to conceive. An entanglement, the two particles are essentially the same reality for a period of time. Entanglement, and then coherence and decoherence. And coherence, I'm not going to address here. It's a very complicated topic. In optics, we tend to use the word, which is really not great for quantum mechanics, that if two light waves interfere with each other, then they're said to be coherent, and that doesn't really do us any good. And I'm going to use the um, example of a human body. So you are you listening to this. Now, if we pull atoms out of you or put atoms into you, you're still you. So coherence is that overall existence or system. And so for the people and decoherence is the breakdown of a coherent system, which doesn't mean you break down, but the quantum mechanical version of you breaks down, and as we said, stabilizes you in space-time. But for people who have a physics background, if we go back to the works emanating in the early 1960s from Glauber, um, if we look at and please forgive me those in non-physics, I may come back to this later, but I'm just going to speak for a few seconds in quantum mechanical terms. So if we apply a number operator for a light beam on the density operator for a light beam, or the wave function for a light beam, we get a change in the number of photons, and we get a change in the if we get a change in the intensity of the beam. But if we apply the number operator to a coherent state, back from Glauber's work, the Nobel Prize, the Nobel laureate for this work, if you remove or add photons to a coherent state, it still remains that coherent state. It's unchanged. So it's very similar to our analogy of a person being a person as you switch out the atoms. But let's try to just get away from those type of experiments, those type of systems, and hit with a little bit more simpler description. So we're going to do non-locality or entanglement, and here the non-locality can exist in Aleutian or Newtonian space, or can exist in Minsky space or relativistic space. And relativistic space or relativity is still considered a classical physics. It's not modern physics, but this was taken from a paper in Nature Reviews of Physics, or it was modified from it. And so let's say we have a photon pair and we have something that, quote, splits the photon pair. But in saying that, I just became inaccurate. And one photon goes in one direction, and the other photon is directed in the other direction at target 1 and target 2. Now these photons were entangled, which means they exist in the same area. They're the same particle for our purposes. And so they're a photon pair. But so they, so no matter how far apart they are, once they undergo an interaction, one of them does, the other one will drop into a state determined by the interaction on the first photon. So that's a very hard concept, but it's actually a core concept of quantum physics. And when Schrodinger developed Schrodinger's equations, he saw it in his own equations. Non-locality is probably the most core feature of quantum mechanics. So can we delocalize golf balls? Well, we're really far away from that. The number of interactions is enormous, and we don't have natural selection helping us in the process. So, but before the other area where we can see quantum mechanics in operation is the incredible molecule. The most incredible molecule I know is cryptochrome. It's the magnetoreceptor in the back of migratory animals, in the back of the eye of a bird, for instance, and it also happens to be part of the circadian clock in humans, and it's found in uh, inflammatory cells, and it is found in other locations. But cryptochrome, first, it requires blue light um, to be activated, and it's one of the reasons why you're not supposed to sleep with blue light on. But the 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 fact about this molecule is it can sense magnetic fields 2 orders of magnitude below the noise limit. And we don't understand how this is possible with this molecule. When the photon is absorbed, it exists in 2 states. You've heard of the Schrodinger cat state, a cat is alive or dead. It's actually maintained in 2 states. And by doing this, and we're not going to go into the actual properties of how it affects, how a field affects it, it allows uh, more sensitivity to a magnetic field than anything man has ever built or anything known. And so, and this was tested, for instance, uh, in birds. If you use a very low field, if the Earth's magnetic field is at 500 nanotensils, and if you use a field of 46 microtessels, then at the specific frequency of 1.315 megahertz, a bird loses its ability in for migration. It loses its ability to sense the magnetic field of the Earth um, and follow the Earth's field to get to a location. But if you think about this, if you were in a stadium that's at 100 decibels and a pin dropping somewhere in the stadium is 1 decibel, it's sensing that pin drop in that shouting stadium of 100 decibels. So again, this paper, which is probably should have just been done in the book, deals with how we overdo this, and we're going to do this with error correction rather than trying to shield it. And that concept, and sort of this concept comes up all the time of when people talk about photosynthesis and then how is it maintained, and suddenly people start using the word shielding. And shielding is a classical concept. It's not a quantum mechanical concept. And I want to get back to where this came from. And this experiment I did in collaboration with Maria Rupnik, Harvard Medical School, Brigham and Women's, and MIT. She actually did the experiment. And for disclosure, we've known each other since medical school, so it wasn't somebody who I didn't know. But I had seen, dating back to the 1980s, behavior in biosystems, which I've now talked to other people through the decades who they've observed, that just doesn't seem to be explainable in by quantum mechanics. And the first two, one were with guinea pig hearts, and if you have two guinea pig hearts near each other on separate and being pumped blood and separate electronic circuits, they ultimately were synchronizing, and that made no sense. Now, I thought of quantum mechanics, but there's reasons why it could be ultra low magnetic fields, or it could have been just dumb luck and it needed to be proven. And had seen things that were suggestive of quantum mechanical tunneling of large molecules through cell membranes. And I'm not going to go into quantum mechanical tunneling is, but uh, uh, the biggest area where I saw it was with leukemic cell lines, HL60 cell lines. So if you would use an agent, an apoptotic agent, induced programmed cell death, just split the cells, induce cell death in one group, then the other group, you would start seeing cell death in it very often, and just didn't make sense. I was not the only. I had talked to other people who had seen it, so we did a small but very well controlled trial. So we split cells, exposed them to a magnetic field, creating a very powerful, both static and electromagnetic field, um, to hopefully disconnect the cells, break up their coherence, and then we resplit them. And then the group, we gave Taxol to T plus, and the T minus cells, which never got Taxol, also started to die off. But the cells that had been broken off because of the electromagnetic field never did not undergo cell death. And this was highly statistically significant. It was only a small study, but it reproduced what we had seen anecdotally for decades. And so whether this doesn't prove that it's quantum entanglement, but it's a good top-down model to start looking for macroscopic quantum effects, because if you let's say these cells contain cryptochrome and they're inflammatory cells, and if you have inflammatory cells distant in the body, if you could link those cryptochrome molecules so that cells in one area of the body knew to respond to cells, would send a message to other cells in the body without any form of signaling to, for instance, this quantum entanglement, that would make sense. That would be useful to the body. Now, again, it doesn't prove that's what's going on, but it's worth us studying it. And but it's these top-down approaches, and the system is exquisitely sensitive. The more you isolate the cells, and it's very sensitive to environmental changes. And I just included paragraphs on magnetoreception and a paragraph on photosynthesis for those interested. Now, I got a lot of my quantum information systems that I applied here by reading textbooks like the one shown in the upper left-hand corner, which is an outstanding book. I'm glad people work in this area. It's relatively easy from a quantum mechanics standpoint to read. Here's an example of a quantum adaptive systems book that can be read by a lay person. We're going to be using quantum optics throughout this. There's a variety of quantum mechanical fields. Particle physics, relativistic quantum mechanics are all fall under the realm of quantum field theory. But we're going to try to stick to photons because they have no mass and we don't have to deal with the studies we're doing with relativistic issues. But if you want to read a really good book, perhaps the greatest physicist of the 20th century, I would say would either be Dirac or Feynman. Sorry, it's not even clear whether it was Einstein or Hilbert came up with the general theory of relativity first, so they did do it semi-independently. But both of these men were brilliant, and Feynman's book, QED, is old, but it is a great introduction for people with no background in quantum mechanics and the incredible strangeness of quantum mechanics. So I hope that's a distractor. We're going to hit non-locality with an interferometer and the path integral, which is just going to sort of hopefully make people realize the reality we live in is very different than the reality we see around us. And this is just a subset. But that's for a later talk. Thank you very much.